Hi all, this is our second class for complex analysis. Today also we'll be dealing with the introduction part for complex numbers. In the last class you have all seen, instead of looking at a complex number as a number of the form x plus iy, we'll be looking at it as an ordered pair x comma y. X is called the real part, y is called the imaginary part. Yeah, so first let's see the algebra of complex numbers. So you'll say two complex numbers, z1 is equal to x1 y1 ordered pair x1 y1 and z2 equal to x2 y2. They are equal if and only if the corresponding real parts and the imaginary parts are equal. That is x1 equal to x2 and y1 equal to y2, obvious thing. Okay, now the sum of complex numbers z1 and z2, which is z1 denoted by z1 plus z2, is defined as z1 plus z2 is equal to ordered pair x1 plus x2 comma y1 plus y2. Let's look at an example. If you add the complex numbers 3 minus 2 and 4 3, you get the complex number 7. 1 7 you get by adding 3 and 4, and 1 you get by adding minus 2 and 3. Product of two complex numbers z1 and z2 denoted by z1 z2 is equal to x1 y1 into x2 y2, which is defined as x1 x2 minus y1 y2 comma x1 y2 plus y2 x1. Okay, if you look at it as this is, maybe you will get surprised, but don't worry, you are familiar with this. You can just think of like z1 is x1 plus iy1 and z2 is x2 plus iy2. Okay, if you multiply, distribute, they use distributive laws, and you'll be getting like x1 x2, then I times y1 x2, and again I times y2 x1, and you'll be getting the last term as I square times y1 y2, but I square is minus 1, so you'll be having the last term as minus y1 y2. Now collect all the real terms and collect the imaginary terms. You know that two complex numbers are equal only when the real and imaginary parts are equal, right? So the z1 z2 has to be equal to x1 x2 minus y1 y2 comma y1 x2 plus y2 x1, yeah, as written here. So let's look at an example. 3 minus 2 times 4 3, if you want to find, that is equal to 12 plus 6 comma 9 minus 8, which is equal to 18 1. Okay, now the difference again, same way as addition. Difference is obviously defined this way. You just subtract the respective real parts and imaginary parts. Here I have given an example. Now like product, quotient is also little bit lengthy to find. So you take z1 and z2 as before, and you call z the quotient z1 over z2. Let it be x comma y. What we want to do is we want to find x and y in terms of x1 y1 and x2 y2. Okay. Okay. Now z1 over z2 is z, right? So you can write z1 as z2 times z. Yeah, here. Now you use the complex standard form for both the sides. So you'll be getting like xy times x2 y2 is equal to x1 y1. Now use the definition of product. You will be having here like x2 minus y2 xy2 plus yx2. This is equal to x1 y1. Now two complex numbers are equal only when the real and imaginary parts respectively are equal. So the real parts, equating real parts, you get this, and equating imaginary parts, you get this. I call this equation 1, I call this equation 2. Now you just have to solve these two equations to get x. Use similar techniques. Here don't forget that here our unknowns are x and y. So these x1, x2, y1, y2, they are just like numbers. Okay, so you multiply the first equation by x2, second equation by y2, and then when you add the second term from both equations will be vanishing, and the first term gets added, right side also gets added, and you get it like this. Okay, from here you get that x is equal to x1 over x2 plus x1 x2 plus y1 y2 over x2 square plus y2 square. Similarly, you get y to be x2 y1 minus y2 x1 over x2 square plus y2 square. Okay, thus z1 over z2 is nothing but x1 x2 plus y1 y2 over x2 square plus y2 square, comma x2 y1 minus y2 x1 over x2 square plus y2 square. So as I said before, you have to make notes every day. Okay, for today I have already sent the written notes to your WhatsApp group. So from there you can um, copy, okay, to your notes. Tomorrow maybe I'll be using the PDF of the textbook I have sent. So then you will have to make the notes. Okay, you can look at my video and you can make notes whenever needed. You can pause the video and then everything will be there on the screen. You just have to copy from the screen. Okay, or you can actually copy from the PDF also. You have it in your group. So do something and get the notes ready. So I have given here an example. You just verify the example. Okay, now see, as I said before, you can look at a complex number in the form z equal to x plus iy, or you can look at it as an ordered pair x comma y. Actually, in the beginning, I have started with this and we changed this into the ordered pair form. Now let's actually the complex numbers were defined in the other way around. They first defined it as an ordered pair and then they saw how it can be identified with this representation. So let's see how we can do that. Now consider z equal to x plus iy. Okay. First note that a complex number is said to be purely imaginary if its real part is 0. Okay. Now the pure imaginary number 0, 1. Okay. This one is denoted by I. You once you fix that notation, see what is I square. So what you have to do is you have to multiply 0, 1 and 0, 1. Use the definition we have given earlier for multiplication of two complex numbers. Using that you get this to be minus 1 comma 0. So we are getting it like I square is minus 1. Okay, so I is nothing but root of minus 1. So this definition of 0 I to be I is compatible with the other definition I equal to minus 1. So it's fine to define I to be 0, 1. Okay, now a general complex number is of the form z is equal to xy. Okay, now this xy you can write it as x0 plus 0y using addition property. Now x0 you keep it as it is, and 0y you split it to be a product 0 1 0y. When you use the definition of product of two complex numbers, you get this product to be 0y. Don't worry. Now 0 1 is our I, right? Now this one is our number x. This one is identified with number y. So this is nothing but x plus iy. So these two definitions, x plus iy or ordered pair xy, both are compatible with each other. Okay, now let's look at algebraic properties of complex numbers. First thing, commutative law, addition and multiplication of complex numbers. The statement is addition and multiplication of complex numbers is commutative. Z1 plus Z2 is equal to Z2 plus Z1 and Z1 Z2 is equal to Z2 Z1. Basically, these two rules can be proved using the commutative properties for addition and scalar multiplication of real numbers. Okay, which you have done before. Okay. Okay. Okay, now let z1 is equal to x1 y1, z2 equal to x2 y2. We just have to show that z1 z2 is equal to z2 z1, which is very easy to prove. z1 z2, you just look at it. X1 y1 plus x2 y2. Just add the corresponding real and imaginary parts. You get this. Now here, this is the crucial step. Okay, now here x1 and x2 are two real numbers. You know the addition for real numbers is commutative. So x1 plus x2 is same as x2 plus x1. So you just change x1 x2 to x1 plus x2 to x2 plus x1, and same thing here. Then when you just split it up, you get x2 y2 plus x1 y1, which is nothing but z2 plus z1. Similar way you can do multiplication also. See here, this is the step where you use the commutativity of addition and multiplication for real numbers. Okay, actually you are using only addition, I think. Maybe you just check. Okay, so here in this step you will be using the commutative property, respective commutative properties for real numbers. Now associative law again follows from the associative law for real numbers. Associative law statement is z1 plus z2 plus z3 is nothing but z1 plus z2 plus z3. You can do in any order. Again for multiplication it is z1 z2 times z3 is equal to z1 times z2 z3. Okay. Now distributive law of multiplication over addition again follows easily from the respective laws of addition and multiplication of real numbers. Okay, now the identity for addition is 0, which is defined to be 0 0, and multiplicative identity is 1, which is defined to be 1 0. Okay, don't get confused. 1 is not 1 1. 1 1 is the complex number 1 plus I, which is not the multiplicative identity for complex numbers. It is 1 plus 0 I, which is 1, which is defined to be 1. Okay, so whenever I say complex number 0, it is actually 0 plus 0 I or 0 0. Whenever I say complex number 1, it is actually 1 0. Actually it's the real number 1 itself. Okay, now see the meaning of 0 being additive identity is that z plus 0 is equal to z plus 0. I mean actually 0 plus z. Okay, that's a writing mistake. It's a typo. Also z into 1 is same as z, which is same as 1 into z. Actually I can skip writing the second one because you already know multiplication is commutative. So you already know that z into 1 is same as 1 into z. Okay, so I don't actually have to write this whole thing, but some structures are there which are in which operations are not commutative. This is a standard way of writing, verifying something is additive identity. So I just followed the standard way. So you can just say z plus 0 equal to z and z into 1 equal to z. So 0 is the additive identity and 1 is the multiplicative identity. Okay, now existence of additive inverse. Additive inverse means if you represent the additive inverse of z by minus z, then what you need is you need the sum of z and minus z to be 0. Okay, so obviously by the definition of complex addition, you will have to take minus z to be minus x and minus y. Then when you add x and minus x, you get 0 here, and when you add y and minus y, you get 0 here. So you get the additive identity 0. So minus z, which is defined here, is the additive inverse of z. Okay, so as you can see here, every complex number has an additive inverse defined in this way. Now existence of multiplicative inverse. As for real numbers, 0 has no multiplicative inverse, right? Similarly, the 0 of complex numbers, which is the ordered pair 0 0, also has no multiplicative inverse. All the other complex numbers will be having multiplicative inverse. Here we will see how to define the multiplicative inverse of a complex number. So yeah, so let's take the complex number z to be xy, and let's define z inverse to be uv. So don't forget, this Z is something you know, and this U and V are something you need to find. So these are our unknowns. X and Y are like numbers only. Okay, now because Z inverse, you call this as Z inverse. You read this as Z inverse. Okay. Okay. You know that you need this. Yeah, as Z inverse is the multiplicative inverse of Z, it is defined here, okay? You need the product of Z and Z inverse to be 1. That's how a multiplicative inverse is defined. Okay. Now, Z into Z inverse has to be 1, right? So, you just substitute here xy times y uv has to be 1. Use the definition of multiplication, you get this. Okay, split it up. You get xu minus yv equal to 1 and xv plus yu equal to 0. That is, since your assumption is xy not equal to 0, 0. So this system will have, you can use Cramer's rule or something. You can see that you can make the coefficient matrix and see that its determinant is non-zero. So whenever the determinant is non-zero, the system will have a unique solution, right? Okay, so the system will have a unique solution. You can use any method, like solving any method which you know like Cramer's rule itself. Or you can just multiply, call this equation 1, equation 2, multiply, subtract, add, do something, and finally you will be getting u to be x over x square plus y square, v to be minus y over x square plus y square. So that Z inverse is x over x square plus y square comma minus y over x square plus y square. Okay, so for today I'll be stopping here. We have seen many properties of complex operations on complex numbers. Okay, all the properties, you go through it, do it again and again, watch the video again and again. If you have any doubt, you can message me in the WhatsApp group if it is a common doubt, or personal message me if it is your particular doubt. Thanks for watching. See you in the next class. Bye.